Hi, good afternoon. I'd like to share with you a progress report on the Seif Project. The Seif Project is intended to solve a problem that we have. A problem with the web. You all heard of the web, I assume? Web? So the web is an amazing thing. It's really wonderful. It has scaled to serve the entire planet, which is amazing. And it's providing a lot of value to humanity, which is also amazing. And it's completely open so that anybody who wants to can create a website, and that's amazing. So unfortunately, there are problems. One problem is that web programming is slow and unreliable, which maybe is good for us because it means full employment for web developers, but it could probably be better than that. The web is a document retrieval system, but it is not a secure application delivery system, which is a problem because that's how we're using it. We're mostly using the web as a secure application delivery system, and it's not working. It's not secure, and it's problematic. And we're securing the web with passwords. And passwords don't work for people. Passwords are easily guessed, forgotten, and stolen. They're not an effective way of securing systems. The original computers were secured not with passwords, but by men with guns, and that was really effective. And that style of security worked until we began networking. When it became possible to access a computer without having physical access to the computer, then security suddenly became a big problem. And the first time-sharing system that encountered this problem solved it by adding a password. It was unlikely that anybody would have more than one time-sharing account, and a person can remember one password, so that worked pretty well. When personal computing started, again, there were no passwords, and that worked fine until we started networking our personal computers together, and then that became problematic. So then we see passwords in our PCs, and we repeat the same thing on the web. Originally, the web doesn't have passwords, but later it acquires them. And good security requires that every relationship that we have has a separate password, but humans can't remember that many. So security was not considered in the design of the web. So the first time we see any mention of security with respect to the web is in the RFC, which introduced the concept of URLs. And that document included the description of a syntax for a URL which contained a password which would be sent in the clear. At least one of the authors of the RFC recognized that this was a really bad idea, and he added this sentence: the use of URLs containing passwords that should be secret is clearly unwise, which is an amazing piece of understatement. But lacking a better alternative, that's what they published. And there were some people who tried implementing this RFC and quickly discovered, in fact, why it was so unwise. So I want to fix the web. But in order to fix the web, we first have to look at what is wrong with the web. And the things that I think are wrong with it are its insecurity, and much of its insecurity is due to its complexity. There's a lot of unnecessary complexity in the web, and whenever systems get too complex, it's likely that they're going to be insecure as well. So I want to look at some of the major systems in the web and critique them and look at what's wrong with them and how we can improve them. But in order to do that, we really have to look at the web and look at what's wrong with it. And this is going to be shocking and upsetting to many of you, that you've spent your whole careers doing nothing but web. It's what feeds your family, it's how you define yourself, and I'm going to say terrible things about the web. I am not talking about you. Okay, this is not about you. This is an objective view on technology. So let's start with HTTP, the Hypertext Transport Protocol. You can view HTTP as being several things. First, it's a text format for expressing key value pairs. It's a rather fussy format. I think there are much better formats available for doing keys and values. It's also a negotiation protocol. The early web browsers were incompetent in terms of media types and other assets. So a browser might ask for a picture, but the picture might come up in JPEG or PNG formats that that browser didn't know how to do. And so there'd be a negotiation that would happen between the browser and the server so they could try to figure out something that the browser could accept. And that negotiation still goes on, even though it hasn't been necessary for maybe a couple of decades now. And then ultimately, the most important thing that HTTP is a request-response protocol, because it was intended to support the delivery of documents. So a user agent will request a document, it'll send a URL, and then it'll wait, and a response will come back from the server, and then it's ready to do the next thing. And if all you're doing is simple document retrieval, that's completely adequate. But that's not how we do things today, because we might have dozens, maybe hundreds of assets within a single page. And using the HTTP protocol, we would go and ask for a script or an image or a style sheet or whatever, and we wait, and a response comes back, and then we can ask for the next one, and we wait, and so on. And so this can be really, really slow. So browsers mitigate this by opening up multiple HTTP connections to the same server so that we can have some interleaving going on so that we can bring the assets in faster, but that's adding more unnecessary complexity. Then there's DNS, the domain name system. DNS was created with good intentions to make it easier for people to assign names to IP addresses, because expecting humans to use IP addresses to connect to computers had serious problems. And so if we could assign names, then users can use those names, and we have a much better time remembering that kind of stuff. Unfortunately, domain names have turned out to be equivalent to trademarks, but the domain name system is extremely incompatible on a legal basis with trademarks. And so there are legal problems that go on constantly there. Also, DNS is subject to security problems. There's domain squatting and similar names which cause confusion attacks, and also there are problems in DNS itself with DNS poisoning and other exploits. There's SSL, Secure Socket Layer. This is something that was developed by Netscape because they recognized that they needed some form of link encryption and authentication in order to do electronic commerce. Unfortunately, the scheme that they came up with is way, way too complicated, very, very difficult to implement. We are still finding serious, drastic problems in implementations of SSL and its successors 20 years after the thing was introduced. If it had been a well-designed thing, then we should have converged on something that's correct by now, and we haven't. SSL is much too complicated. The thing that I like least about SSL is its dependence on certificate authorities. Certificate authorities are private agencies which, for a fee, will generate a cryptographic certificate which asserts that some thing is associated with some other thing, usually the name of a company or a domain with a public key or something like that. I don't trust this system. The principal company behind this stuff is VeriSign. And should I trust VeriSign? I don't know. I don't know what goes on in that company. I don't know why I should believe that that company should be the root of all trust. But even if I trusted them, there are hundreds of other certificate authorities which your browser trusts equally, many of whom have been corrupted. And who knows if the others have been corrupted yet? We just don't know. So I don't like having to depend on things that I cannot possibly know. Then there's HTML, the hypertext markup language. Is HTML a good thing or a bad thing? Well, that depends on what you're trying to do. If what you're trying to do is to create a simple technical document and be able to present it on someone else's screen, it's really not very good. The HTML language is fussy and difficult to write. It's why we invented markdown languages. Wikipedia works because it accepts markdown languages, which are much, much easier for people to deal with than HTML. Now, on the other hand, if what you want to do is create a container for the delivery of secure applications, it's really awful because it wasn't designed to do anything like that. And a lot of clever people have figured out ways to try to make it do that, but it's not really fit for that purpose, and that's why a lot of the things that we do are much more difficult than they should be. We've spent a couple decades now trying to figure out what's the best way to write applications that are delivered in the form of HTML. And the thing that seems to work the best is templating. And I really don't like templating. Templating is the attack vector of XSS attacks. And while it's possible to do templating without subjecting users to XSS attacks, nobody seems to have been able to do that yet. XSS seems to happen almost every day. It's also a trap that if everything is directed toward HTML, everything becomes HTML. The servers become dependent on HTML. The database has dependencies on HTML. Everything is HTML. We're never going to get rid of it. Then there's the DOM, the Document Object Model. This is one of the worst APIs ever imagined. It's just really difficult to use. It's really fussy. It's not nearly portable enough. It's at the wrong level of abstraction. It's way, way too difficult. It's also horrendously insecure because every node is linked to every other node. So if an attacker can get access to any node, they get access to everything. And there's CSS, crappy style sheets. I don't think I need to tell you what's wrong with CSS. And then finally, there's JavaScript. JavaScript is a hot mess. JavaScript was designed in 10 days. It turns out you can make a lot of mistakes in 10 days. But there is some brilliance in this language, which is surprising and amazing, remarkable, but in fact there is some goodness in it. So I'm not the first person to have observed that there are these problems in the design of the web and suggested that we could do better. And in fact, Microsoft, Apple, Adobe, Oracle, and many other companies, large and small, have all looked at this as an opportunity, that they could create a new platform that could displace the web and turn it into a proprietary system or replace it with a proprietary system. In most cases, the technology that they were offering was clearly superior. Unfortunately, in most cases, the solutions they were proposing were not open. They were trying to capture the web. And so I'm glad that they all failed at capturing the web, because the fact that the web is open is the thing that I like the most about it, that anybody can create a presence on the web and do stuff, and they do not have to make a deal with any other company. They can just do it, and if they can get attention, then they can be successful with that. They don't have to share their revenue or pay fees or taxes or bounties or tribute to anybody else. And I really, really like that. And so whatever else happens with the web or attempting to replace the web, I hope it has that same property. So the reason the other systems, the other neo-webs or web replacements didn't succeed wasn't because they weren't better, because I think all of them were better. It's that they didn't have an adequate transition plan. So later I'll show you my plan, and hopefully you think it's a better plan than what they had. Their plan was to convince you. If they could convince the developers that they had better technology, then they would win. And that turned out not to happen. So my plan is to upgrade the web. I don't want to replace it. I don't want to capture it. I want to keep it doing the things that it does well. And in fact, there are some things that the web does extremely well, and I don't want to change any of that in any way. What I want to do is to fix the things that it doesn't do well. So that brings us to the Seif Project. The Seif Project is a radical, minimal, secure, open system. It's architecturally very different than the old web, but it can be delivered through web browsers. So the user experience should not change. Customers are not given passwords in the Seif system, which eliminates one of the biggest sources of insecurity, because if you don't have a password, you cannot be tricked into revealing your password. And so we get much greater convenience and much greater safety. Instead of using passwords, we're going to be using public key cryptography for authentication. And we're not going to be using certificate authorities because they're not trustworthy. So we're doing the Seif project in 5 steps, 5 parts, and I'd like to show you each of the parts. So part 1 is SafeNode. SafeNode is a module adding cryptographic services to Node.js. It provides it's not a complete general purpose cryptographic library. It's only providing the services that Node itself needs, which includes elliptic curve 521, which we use for authentication and key exchange, AES 256, which we're using for block encryption, and SHA-3 256, which we're using for secure hashing. We're also providing a very good source of randomness. That one place where many hopefully secure systems have fallen is that the quality of their random numbers were not good enough. And so we're taking a lot of attention to make sure that we get sufficient randomness. The way we're doing that is we're providing entropy collection services. So we're going to harvest entropy from the operating system if it has some to provide. But I don't trust operating systems to provide us with enough entropy. And so we're also going to use your microphone. So with your permission, we'll open your microphone for a few seconds just to listen to noise. We're not going to record it. We're not paying any attention to it. We're just going to take all the noise that we see and hash it and try to produce some entropy from it. We'll also do the same thing with your camera. With your permission, we'll turn your camera on. We'll observe a couple of frames. Again, we're not even looking. We're just looking for noise in the signal, and we'll take that noise and we'll harvest it and then save it, and that will become the basis for the random numbers that we're going to generate. We need that randomness because we're going to be using elliptic curve 521 public keys as unique identifiers. And the way that you prove that a public key is yours is that you have the private key, which corresponds to it. And we want you to be able to generate that key pair yourself. I don't trust anybody else to give you a key pair. I don't see a secure way of doing that. So instead, you're going to make your own key pair, and we're going to give you the tools which will allow you to do that securely. And we want these keys not just to be unbreakable and unguessable, we also want them to be globally unique. And with 521 bits, with sufficient entropy, I think we can do that. There's a very smart guy named Zuko who has a theory about names. He identified 3 useful properties of names and thinks that you can get at most 2 of them in any name. So of these, the web decided to go with human meaningful, at least to the extent where you think a URL is human meaningful. But I'm more concerned with security, so I'm taking the other 2. I want to have names which are securely unique, and that's why we need the good entropy in creating the keys, and also globally decentralized, which means that you make them yourself. There is no global registry which will assign these numbers. You create it on your own. But the consequence of that is that they're going to be huge things which will not make sense to humans. Part 2 is the Seif protocol. The Seif protocol is secure JSON over TCP. And unlike HTTP, which is designed to do document retrieval, the Seif protocol is designed to implement efficient sessions. So it wants to send messages and receive messages. And a message doesn't need to be responded to, and messages do not need to be requested. If the server has something to say, it'll just say it and say as many things as it needs to. If the browser has something to say, it will just say it and not necessarily wait for a response. So cryptography is used in the implementation of the Seif protocol. And to review, we use 2 forms of cryptography. There's symmetric cryptography, in which the same key is used for both encrypting and decrypting. And we also use asymmetric or public key cryptography, in which a public key is used to encrypt and a private key is used to decrypt. So this is the handshake that we use to create a secure connection on the Seif protocol. So at the beginning, we have Alice and Bob who are about to connect to each other. Alice has a public key and a private key. Alice knows her private key because she is Alice, and we hope that nobody else knows Alice's public key. Alice also knows Bob's public key, maybe because she got it from a directory or some other source. Then Bob has his own public key and his own private key. He has his private key because he is Bob. Alice then generates a random handshake key. This will be a completely random 256-bit key, which we're going to use for the handshake. And she creates a message, which will get sent in the clear. It's just a JSON packet. First identifies itself as a safe message, and the version of the protocol that we're using at first is version 1. Eventually, we may discover problems in something, maybe in the cryptographic algorithms or something, and we'll have to upgrade to stronger crypto. In that case, it'll become safe too. Then we also send the handshake key encrypted with Bob's public key. And we use the handshake key to encrypt Alice's public key. And that gets sent to Bob. Bob receives that message, and because he has his private key, he's able to decrypt it and recover the handshake key. And now he has a handshake key, so he's able to decrypt Alice's public key. So he now knows who is trying to connect to him. If he has already a relationship with Alice, he now knows this is Alice, and so there's no additional login needed. So Bob now generates a session key. This is another 256-bit key, and he uses that to create another message. So he creates a message, or he creates a JSON message which will contain his session key encrypted with Alice's public key. And that entire message will be encrypted with the handshake key. That will then get transmitted to Alice. Alice has the handshake key, so she can decrypt the package, and she has her private key, so she can decrypt the session key. That session key will now be used for all remaining messages in this session. We have just set up a secure authenticated connection in one round trip, which is pretty close to optimal. So it's a very, very low overhead. It has very nice security properties. For example, a man in the middle cannot see what's going on unless he has access to both private keys. The Seif protocol is a full duplex protocol, meaning that either party can send at any time, and they don't have to wait for the other to respond before sending the next message. This will allow us to take much better advantage of the network and to have higher performance applications. We provide two forms of message send. There's the normal send, which will have automatic persistent retry. So it's not guaranteed delivery, but as good as we can make. So if there's a network partition, which happen fairly frequently in mobile applications, we will persist those messages and we will attempt to resend them when the connection is reestablished. There's also a status send, which is provided for telemetry and gaming, which will just send the latest version of this message. And if it fails to go through, we don't care. Or if we start to get behind, we'll throw away the old messages. We just want to send the last one. This is most applications don't want this, but games and control panels and things like that really want to see the current value and don't want the current value delayed for values which are no longer of interest. Part 3 is safe resource management. So this will be a system for accessing resources by hash codes. The initial motivation for this was secure delivery of programs, but we're going to use it for everything. So any blob that you want, we'll take the cryptographic hash of it, and that becomes the name of the blob. So if you ask for that, then we will deliver that thing, and the thing that you receive has to match that hash code, otherwise you know it's been tampered with. One of the nice things about this is that it doesn't matter where you get the blob. So there are really interesting opportunities for caching and distribution. So it's a very efficient and very safe way of distributing resources. Part 4 will be safe apps. It'll be an HTML-free, JavaScript-based application delivery system built on Node.js and Qt. And you guys know Qt? Qt is an application system that was developed in Norway. It was part of Nokia for a while. It is now an open source thing. It's brilliant. It's a really nice way of making apps. And we're going to be using that in order to make things in the Node system. So here's the block diagram. So Seif app has two parts. There's the Node part where we do logic and connection and persistence, and the Qt part where we do user interaction and display. And we have very strict separation between those two aspects. So the Node server that we're using here, or we're using Node as a client here, and we've stripped it down considerably. So we've removed almost everything from Node except for the event loop and the HTTP stack. I'm sorry, the TCP stack. We removed almost everything else, including NPM, because we're trying to make this very, very secure, and so in order to do that, we're trying to make it very simple. And NPM doesn't match our security model, because NPM wants to allow anybody to load anything from anywhere that can do anything. And if you're concerned about security, you really don't want that. So we're going to have a different way of loading stuff based on the ES6 module manager. Each half, the Node half and the Qt half, will both be running JavaScript engines. Each will have its own event loop running its own threads. They'll both be running simultaneously, and they communicate through a JSON channel where you can post messages from one to the other. Even more interesting, we can allow presences from other parties, other companies, to be running in the same environment, interacting with them. So I can do mashups, and I can finally do them securely. So I can have another site involved in the application with confidence that it can't corrupt us and we can't corrupt them, but we can communicate and cooperate in order to serve the user. I think that's going to be one of the most important aspects of this system. We're also going to be providing trust management, because we know that humans cannot manage 521-bit keys, and so we will allow them to assign pet names to them, and we will store them for them. We'll allow them to put them in the cloud, but they'll be properly encrypted in the cloud so that no one can get access to them except themselves, and that they can be shared over all of their devices. So if you have any device, all of your devices will be able to share all of the relationships that you've had in the Seif system. Then part 5 is the Seif Helper app. This is where we take the Seif app and turn it into a helper app that can be run in a web browser. Anybody remember helper apps? Maybe? Not even the old guys? So when Netscape first came out, Netscape didn't know how to do a lot of things. So they had a concept of a helper app. Like if you wanted to display a JPEG, Netscape didn't know how to display JPEGs. You could say, when you see a JPEG, open my Paint program, and my Paint program will display the JPEG. It turns out that interface is still in all the browsers. It still works. You can go into the control panel and you can find it. So we're going to use that initially. So this will allow you, as developers, to download our helper app and integrate it with your browser, and then you can see what it's like to run Seif in your browser. Now, I don't expect normal people will do that. In fact, I'm pretty confident normal people won't or can't do that. But that'll be sufficient to allow you to get an early look at this. Eventually, we'll want the browsers to integrate it, but there's some things we have to do first. So here's my transition plan. This is why I think the Seif project can be successful. So step 1, I need to convince one progressive browser maker to integrate the Seif Helper app into their browser. It should be an easy thing for them to do because we don't need to be tightly coupled to the browser. All we need is a rectangle where we can put our pixels. We need access to UI events, and we need a JSON channel where we can talk to the browser and send messages back and forth. That's all we need. So it should be pretty easy to do that. I don't know which browser maker will do that. I'm pretty confident it won't be Apple, and probably won't be Google. It might be Mozilla. Mozilla used to be the technology leader in the web, but they've fallen way behind in recent years just because they can't afford to compete with these other really rich companies. But this might be a way for them to kind of leap ahead, and they might want the opportunity. Might also be Microsoft. Microsoft was also a technology leader in the web, and they also fell behind. And recently they've gotten back up in terms of technology. You know, they're like the edge stuff is really, really good. And nobody cares. It just doesn't count. It's like they didn't do it. So they might be looking for some way to get some credibility, to get some recognition for what they did. So maybe they'll want to do this too. So hopefully we can get one browser maker to integrate. Then we have to convince one secure site to require its customers to use that browser. So it could be a bank or a financial institution or a healthcare institution or a government or somebody who is scared to death of doing business on the web but is having to do it because that's where everybody is, who are looking for a safer alternative. And if we can convince one of those to try this, then we'll have completed that step. Then risk mitigation will compel other secure sites to do the same thing. And I liken this to penguins. Penguins are on the ice, and they've been out there all winter, and they're getting really hungry, and they're looking over the edge, and they know there are fish down there, and they want to jump down and eat the fish, but they also know there are leopard seals and sharks and things down there that eat penguins, and so they're really cautious. And they all walk up to the edge, and they're all getting closer and closer and pushing, and eventually one of them slips and falls in. And then everybody looks, and if he comes back up, then they all jump in. So I'm hoping this will go like that. If we can convince one company or one project to do this, and if it's successful, I'm hoping then others will want to do that as well. If that succeeds, then competitive pressure will move the other browser makers to do that as well. Not everybody wants to be first, but I don't think anyone will want to be last. So if this turns out it's actually going to go, I think everyone else will want to implement it. And then the world will follow for improved security and faster application development. So everybody who's doing applications which could benefit from the security that Seif provides will want to do it as well. Also, they might want to do it just because it'll be an easier application development model. But nothing breaks. So we're not suggesting that anything which happens now stops happening. In fact, the way that the web works for providing introductions is brilliant, and I don't want to change that. The way the web works for searchability is brilliant, and I don't want to change that either. But once you have established the relationship, once you're committed and you want it to be secure, then Seif is the way you want to go. So whenever you're talking about software security, there are obviously a lot of difficulties involved. You have to make it do what it should, which is always a problem with software. We rarely get that right. It shouldn't do what it shouldn't. That turns out to be even harder. And that's one of the big things we have to do with secure software. So making boasts that, yeah, we're going to knock this thing out and solve all the world's problems, it usually doesn't work that way. No software is initially secure, and I don't imagine ours will be either, even though we're working really hard to try to make it so. I expect that we will be very embarrassed when this stuff comes out, because there's stuff that we'll have overlooked or screwed up, and we're hoping that you'll point it out very quickly and pleasantly, and then we'll fix it. And I'm hoping eventually we converge on something which is secure enough. I think only a minimal approach can do that. Up to this point, we've been seeing maximal approaches, and the maximal approach does not seem to converge on security. So there's nothing new here. There's no new science, no real invention. Much of our model is based on object capability theory, which has been around for many decades. We're just factoring it and turning it into something which we think can work practically in the modern web. So this is where we are. We finished part one. So part one, we published a couple years ago. We unveiled it at OSCON. Seif Protocol we introduced in 2015, also at a different OSCON. And so those are both open source and freely available. You can go out to GitHub and look at our stuff. If it makes sense to you, you can adopt it, use it for any purpose. It's a completely open and unrestricted license. If you'd like to help us, we'd be very glad to have your help. We're currently working on the Seif Resource Management System, and hopefully we'll have something to say about when that'll be available. And then we'll continue working with the Seif apps and the Seif Helper app. So if you want to see this stuff, you can go to safe.place, and that'll direct you to GitHub. So the goal of the Seif project is to provide safe and effective relationship management on the web. And because of our particular approach, I think there's a chance it could work. So please check us out. Thank you very much. So we have some time for questions, if there are any questions. Yeah.
How will you know when you've succeeded? I'm a very cynical person, but as you pointed out, other people have tried and failed. Do you have if your transition plan doesn't gain traction, do you have a plan B yet?
So how will we know if we succeeded? And when we don't, what is plan B? I think that, well, my end goal is to build the whole thing. But I think the Seif protocol could have applications immediately. I think maybe the Internet of Things wants to be connected over Seif and not over HTTPS. So it may be that we can salvage one chunk out of it and get that fully deployed before we can get the rest of it done. And there may be other spin-offs of the project which are also beneficial even if the entire thing doesn't find adoption.
It seemed to me that you could have also kind of gone for the mobile approach, because wouldn't it be kind of easy to just have a Seif app and then other provide, if I wanted to write a plugin, some kind of content for that Seif app?
Yeah, he's asking why didn't we go the mobile route of making the Seif app a mobile framework. Because the mobile environment isn't as open as we like, and we're going to try to push for the open thing first. If we fail to get adoption in the open thing, then maybe we'll try to go into the marketplaces. But that's the way we're going right now. Yeah, we're not religiously focused on anything. We're just trying to be pragmatic, and so that's the way we're going. If it turns out plan A doesn't work, then we'll certainly look at plan B, and then C and D, however many letters it takes. Yes?
So the way that I understand this is you're building this basically based on JavaScript. So there are people in the world that don't really particularly like JavaScript and want to work in other languages.
Yeah, including me.
Yeah, fair enough. So I suppose it's not worse than the situation that we have today, based on you need to do JavaScript on the client side. But if I understand this correctly, you could also implement the Seif protocol using other languages on the server side, couldn't you?
Sure. Seif protocol is completely language agnostic. It's JSON on TCP, so yeah, we could do that with anything. And so we're working on bindings to Java and iOS because we want to enable exactly that.
Good. Sounds good.
Yeah. The JavaScript dependency doesn't happen until you get up to level 4. So levels 1, 2, and 3 are JavaScript independent.
Although you have Seif nodes, which sounds very
That's implementation, but basically it's just a crypto library, and and most of the crypto library is taken from other open source sources, and so you could very easily, in fact, we're doing that. We're implementing it for other platforms. We're starting with Node because that's where we live, but yeah. Okay. Yeah.
Early on in your talk, you mentioned CSS being a bad thing. So, do you suggest any alternatives to this?
So we're going to be, instead of using CSS, we're going to be using the presentation capabilities that are built into Qt. That stuff's programmatic, and I think it'll just be an easier thing for us to deal with. CSS was not designed to do the stuff that we do. It was designed for document formatting. And it's really a struggle, getting all the rules to line up. And CSS was designed with the assumption that there would be a single author or designer responsible for the entire document. But that's not how applications work. Right? We've got lots of things from lots of sources, and they all have to get integrated. And doing that in a way where the styles don't conflict with each other turns out to be way, way too hard. So we think we can back off of that and come up with something that's much more straightforward. Yes?
What's about upgrading the encryption mechanism in the future?
Yeah, so we need to be able to upgrade the encryption in the future. I'm not confident that the quantum computing thing is going to work out, but if it does, or if there's some other problem and we find that the algorithms that we've selected are not going to be good enough, then we're going to have a transition plan. So using the safe flag in the initial message, servers will be able to say, you need to be coming to us at this level or not. We're going to be much more coarse than SSL has been. SSL has a negotiation framework built into it where both parties can agree on what level of cryptography they want, which serves the man in the middle, because the man in the middle can say, I want the weakest thing available, and so they can dictate that. We're not going to be doing that, so we're going to be much more brittle. So I think we can manage that. I don't anticipate that we're going to have to change crypto levels very often. I'm hoping it's going to be like a once-in-a-lifetime event, not something that happens every year. Yes?
You mentioned a few times about the application development model becoming easier, and you gave me one example already about CSS going away. So what are the other things that I currently have to do that will go away or become easier that will kind of convince me to you attacking from the other end?
So I think moving away from HTML, I think that's been a trap, and so we'll get rid of that. Having two event loops, I think, is going to be interesting. So you don't have to worry about as much about stuff blocking in either loop, because all the stuff is independent of all of that stuff. And because we have enforced separation between state management and presentation, it's going to force cleaner application architecture than we see currently, where you see logic somehow getting into the display layer and all of that stuff. So we're going to force separation there. And so I think that'll also lead to better development. Yes?
You talked about possible browser vendors that might adopt Safe first.
Mm-hmm.
And then you talked about the first application possibly being a financial company or anything like that. Do you have anyone in mind or any idea of who that first customer would be?
So who do I have in mind to be the first application that runs? Yeah, I have someone in mind, but it would be unrealistic for me to ask them or anybody to commit at this point, because we're still vaporware. And so until we're much further along, it'd just be irresponsible for me to even have that conversation. So, ask me in some unspecified time in the future, and maybe I can give you a better answer. Anybody else? Okay, I think we're done. Thank you. Oh, and don't forget to drop a green card on your way out.